I spent, I did that before where I recorded and didn't record for a class. So thank you. I think that was Jacob. Okay, so we're talking about complex numbers and phasors, the mathematics of AC. So somewhere in your life you were taught the number line. So let's go to the number line. Maybe second or third grade, they showed you the number line. And they drew these two arrows on it like that. And I can put a mark here if I call that 0. Then I can start counting to the left and to the right like this. And these, of course, represent numbers or quantities. You know, the farther I go to the right, I get bigger positive numbers. The farther I go to the left, I get bigger negative numbers. This number line is called the real number line. So any quantity on the number line is a real number. Now I want you to think about something though. I'm going to talk about something that you may or may not know. Let me come over to like the number 3 right here. So this is a 3. So I got a 3 here and I got another one. 1, 2, 3. I got one right here. Okay. So if I write this number 3, the way I write it 3 with a plus sign in front of it. If I write this one, I write it 3 with a negative sign in front of it. Well, this sign right here, that positive sign, that's called an operator. The negative sign is an operator. You're familiar with operators. You know addition, subtraction, multiplication. Those are operators. Sometimes operators operate on 2 numbers, and sometimes operators only operate on 1 number. So what this does is it tells you that that 3, to get to it, I have to go to the right, and this one I got to go to the left. I want to introduce something called phase. This is what may be new, phase. It turns out that every number has what we call phase. And when you learned about the number line, you probably did not learn about phase because you didn't need it. Because, well, basically it works like this. If I want to get to that number 3, I can count over like I did, 1, 2, 3. But I can draw an arrow that's 3 units long, like this. I can draw an arrow that's 3 units long, and then this axis right here from 0 over to the right. If that's my standard or my starting point, say my starting point, then I can do the 3 like this. I can say I go over 3 units, and the angle that I make with this axis right here is 0 degrees. And that's what I mean by phase. Phase is an angle associated with a quantity or magnitude. So the phase of this is 0. If I want to get to this other number, -3, what I got to do, I still go over 3 units. So I go 1, 2, 3 units to the right. But then what I can do is take that arrow, that's 3 units, and I can move it over like this. And now I'm pointing at the -3. So now my arrow is over like this. But to get it over there, what I had to do is I went over 3 and I had to move it over all the way over here. And you know that's 180 degrees. So the way I would write that is I would say I went over 3 units, but my phase is 180 degrees. So all quantities have phase. And if you never heard of phase, it's probably because you didn't need it. Because most of the time when we deal with numbers, we're working on the real number line. So you don't really need the concept of phase. Phase is actually hidden in this plus sign and that minus sign. When you write a +3, what you mean is 3 with a phase of 0. When you write -3, what you mean is 3 with a phase of 180. And so if we're working on the number line, we have no reason to bring this up, because if we're working with either 0 degrees or 180 degrees, then we can add and subtract numbers and we're on the same line, so it works out pretty well. And that's okay. The problem is, as you'll discover real soon, is that in AC, there are quantities that exist in nature that don't have a phase of 0 or a phase of 180. And so we have to be able to talk about those quantities. there are quantities in AC that have phase of 90 and negative 90. Well, I'll show you exactly why it is those values and what those quantities are. But there's quantities in AC that have angles of 90 and negative 90, and so we need a number, we need a system to deal with that. And there are even quantities that have other phases in between those, or anywhere in the unit circle. And so how do we deal with numbers that do not have a phase of 0 or a phase of 180? Well, I want to show you that. Before I show you that, remember that when I write a positive 3, notice I write the operator first and then the magnitude. When I write a negative 3, I write the operator first and then the magnitude. And even though you probably didn't think of it like this, what you mean by positive 3, you mean the magnitude of 3, and this right here is the phase angle, which is 0 degrees. When you say negative 3, what you mean is the magnitude of 3, but that negative sign that I have written first before the 3 represents a phase angle of 180. So I want to introduce you to a coordinate system that's a little different. So I'm going to start with my real number line, just like before. So these are real numbers. And I go to the right, I get bigger positive numbers. I go to the left, I get bigger negative numbers. And right here, if that's 0, then I know everything to the right of 0, that of the origin, I'll call it the origin. Everything to the right of the origin, I'll put a 0 there just for giggles for right now. Everything to the right, every quantity to the right of the origin has a phase of 0, and that's indicated by that plus sign. Every quantity, every number to the left of the origin has a phase of 180, and that's indicated by that negative sign. So now what I want to introduce is another set of axes. Remember, this is the real axis. These are real numbers, so that's the real axis. Well, I can actually make another axis like this. And this is called the imaginary axis. I'll just do IMG for imaginary. That's the imaginary axis. And just like with the real axis where we have an operator that represents an angle, I want to have an operator that represents an angle here. Now in math, when they talk about imaginary numbers, they use I. They use I. Well, obviously we cannot use I in electrical engineering because I stands for current. So in engineering, electrical engineering, instead of I, they use J as the operator. Now that I is just what you think it is. That came up in math because they want to be able to take the square root of like a negative number like that. Take the square root of a negative number. And you know you can't do that. I can take the square root of 9 all day, right? I can take the square root of 9. I know it's 3, but if you try to take the square root of a negative number, then you get an error in your calculator because you're not allowed to do that. So somebody realized that if I have a product like that, then I can take the square root of A and multiply that by the square root of B, and these two sides are equal. So the way they get around that is they say, all right, let me break this up. Let me break this up into 9 times negative 1. And then I'll take the square root of that and the square root of that, applying this principle from math. Well, the square root of 9 is, of course, 3, but you can't take the square root of negative 1. It's impossible to do that. So they hid it. They said, you know what? Let's call that I. And so you write this as 3I. It's in math, they wrote it like that, it's 3I. And you know, if you took I and squared it, if I take this and square it, then I get I squared. That undoes the square root. It will undo the square root. I get negative 1. Well, we use J for that. We can't use I because we use I for current. We use J for that. So that I not only represents the square root of negative 1, that I is an operator and it has an angle associated with it that I'm going to show you here in just a second. So this is the real axis. Any number on this axis is called real numbers. And the one that goes up and down is called the imaginary axis. And any quantity on the imaginary axis is called an imaginary number. Now, let me pause for a second and talk about the name imaginary, because I don't want you to be confused at all. That's probably a bad name, imaginary, because when you think of imaginary, you think not real. Like mermaids are not real, unicorns are not real, they're imaginary. But these numbers, even though they're called imaginary numbers, they are real quantities. If you took your real finger and stuck it in an imaginary 4,000 volts, you will die. There's nothing imaginary about that voltage. And so the imaginary, that's just the name that we give them. Well, just like I have a positive operator, I call it, represents 0 degrees, and a negative operator here that represents 180. On this imaginary axis, we use not the I, because I is for current. We're going to use the J operator. So this is a plus J, and this is a minus J. And now the way you want to think about this is the operator tells you the phase. If I have the operator like this, then the phase is 0 degrees. If I have an operator like this, then the phase is 180 degrees. If I have an operator like this, then the phase is 90 degrees. If I have an operator like this, then the phase is 270 degrees or minus 90 degrees. Now, remember when I had 1, 2, 3, when I wrote that number 3, what I did, I put the plus sign and then the 3. I wrote the operator first and then the magnitude. Or when I did negative 3, I wrote the operator first and then the magnitude. Well, if I had an imaginary 3, I would write the J operator first and then the magnitude, just keep it in line with this right here. As we do this, we do that. That operator is just like the plus sign or the minus sign. It just so happens that if I have a plus sign, the phase for that quantity or that magnitude is 0. If I have a negative sign, the phase is 180. But now I can handle phases of 90 and negative 90 if I use that J operator. So the phase of this represents, if I have it like this represents the magnitude 3, but the phase angle is 90 degrees. Or if I go down here to minus J3, that represents, again, the magnitude of 3, and the angle will be a minus 90 degrees or 270. Usually when we write the angle here, we measure from here counterclockwise, but if I go through the smaller angle, I go clockwise, I just call it a negative angle. So you remember from trig, and going around here, 270 degrees is exactly like going from here the other way, but that's minus 90 degrees. If you took the sine or cosine of either one of those, minus 90 or 270, you get the same number. So that's equivalent. That rotation is equivalent. So let me be clear on what I'm saying. This coordinate system, you know, 2 lines make a plane surface. So this coordinate system that I'm showing you is called the complex plane. The complex plane. In the complex plane, any number that's on the horizontal axis, the real axis, is a real number. In the complex plane, any number that's on the imaginary axis is an imaginary number. And all I mean by real number is the phase is either going to be 0 degrees or 180. And all I mean by imaginary is the phase associated with that magnitude is going to be positive 90 or negative 90. So I can have real numbers and I can have imaginary numbers. But think about this for a second. What if I'm not on an axis? I know if I'm right here, that's a real number. So let's just say that's A. That's a real number. I know if I'm over here, we'll just call that B, that's an imaginary number. But what if I'm right there? I'm out here and this is quadrant 1, 2, 3, 4. We count back that way counterclockwise. What if I'm right here in quadrant 1? I'm not on an axis. What kind of number is that? Well, when you're like that, what you have is 2 parts to the number. You have a real part. That's the A. and you have an imaginary part. That's the B, and we usually put a J in front of it so that we know it's imaginary. So if I have a real part plus an imaginary part, that A plus JB, we call that a complex number. A complex number. So a complex number is a number that consists of a real part and an imaginary part. So this over here, I'm going to just call it C for complex number. So a complex number might look like this. 2 plus J3, or minus 5 minus J2. Those are all complex numbers. A complex number has a real part. We usually write the real part first, and it has an imaginary part. The imaginary part, we show the phase with that J operator. So, two ways to think of a complex number. Two ways. Way number one, a complex number is a number that has a real part and an imaginary part. Or you can say a complex number represents a point in the complex plane. A complex number is a number that represents a point in the complex plane. Now, don't forget why we're doing this. Let me go back, because I know this is not hard at all. It's really simple, especially since you can relate it to a regular XY coordinate system. But it's new, so it may seem a little funny, but I want you to know it's necessary, and here's why. It's what I said before. Most of the time, we deal with numbers. What do we deal with numbers? We deal with numbers when we count money, if I measure the temperature, if I no matter what I do, normally we're dealing with a real number. 99 times out of 100, 999 times out of 1,000, we're dealing with real numbers. So I don't need any of this stuff. But if you're in engineering, especially electrical engineering, God gave us these quantities that are not real numbers. God gave us quantities that don't have a phase of 0 or 180. God gave us some quantities that have a phase of 90 and minus 90, and God even gave us some quantities that have phases that are out here in these other quadrants. So we can't use regular real numbers to represent those numbers. Now don't worry about what they are. We'll get to that. We'll get to that. But just look at the math that we got to use to represent those kind of numbers. So a complex number is a point in the complex plane. A complex number consists of a real number and an imaginary number. Now let me clean this up a little bit because I want to show you something else. There's actually two ways to write a complex number. I already showed you one way. I want to show you the other way. So let me clean this up a little bit. All right, so we'll go back to my complex plane. So here's my real axis. Here's my imaginary axis. Now, let's say I want to get to this point right here. So that point, if this is the real axis and that's the imaginary number axis, then that point represents a complex number because a complex number has a real component and an imaginary component. So let's say that this distance right here, from here to here, let's say that's A units, and the distance right here, from here to here, let's say that's B units, but I got to put a J in front of it so you know it's imaginary. So if this is the point C, one way to get to that point, you can tell me how far over to the left or to the right to go on the real axis. You say go to the left or to the right A units, and then you can tell me how far up or down to go on the imaginary axis. You can say go up so far on the imaginary axis, go up B units. So I say plus JB, and I can get to the point C, and that's a complex number. But here's another way. You guys know what do they call it? A compass. It looks like you use it in math. It looks like that. Has a sharp point on it, and you can put a pencil right here. I think it's called a compass. Pretty sure it's called a compass. But you can stick it here and you can make a circle with it. I had one of those in like the second or third grade. I haven't seen any one of those things in years. But you can draw a perfect circle with it if you stick it in there and you turn it around the circle. So imagine I had a compass, and what I do is I put an arc through here. I just put an arc through there like that with the compass. So I get the compass, I open it up, and I just put a little mark through there like that. So now what I do is, if I bring that arc down here like that and make kind of a circle, if I start at the origin and go out and touch the circle, that's the radius of the circle, of course, right? So if I go from right here and I go over a distance r, then that would be the radius of that circle. So one way to get to that complex number is to go over a units and up JB units, or if I draw an arc through the circle, through the point, and I make a circle, I can go out, and this is called a radius vector. That's a radius vector. So tell me how long to make the radius vector. It's just the radius of the circle. And then you got to tell me how many degrees to lower it up or down to get to that point. So I go out r units, that's my radius, and I go up that many degrees. And so my radius vector is actually pointing right here at point C. And this angle right here, theta, is how far you told me in degrees to go up. Now remember what I said last time we were together. We measure in degrees and we calculate in radians. So anytime you see a sign of an angle, you better have your calculator in radians. But when you're doing something like what I'm doing now, we're actually going to measure that angle. You would do that in degrees. You're not actually going to measure the angle. This is just math stuff. This is all theory. But you will have to do calculations with radians. So we'll get back to that later on. So my point is this, though. I can get to that number C. This is C. That's the complex number C by going over A units and up JB units, or I can go out R units, and I can take that radius vector and raise it up so many degrees. So it's going to be R, and this sign right here, that's R at an angle of theta. So I can actually get to C that way. I can go over and up, or I can go out the radius vector, and you tell me how many degrees up or down to move that radius vector. And if I'm pointing at that point C, then that's a complex number. I can do it this way. Anytime you see a complex number with a J in it, we call that form rectangular. I'm just going to abbreviate. This is the rectangular form of a complex number. So if it has a J in it, it's a rectangular form. The reason it's rectangular, because if you go over and up, I can make this rectangle thing like that, and then that diagonal gets me to the complex number. So that's the rectangular form of a complex number. If you see an angle, instead of a J operator, if you see an angle there, then we call that the polar form of a complex number. So we got this complex number. Complex number has a real and an imaginary part, and we can express it two ways. We can express it in rectangular form as A plus J something, JB in this case, or we can express it in polar form. That's when you have a radius vector and you have an angle. You tell me how many degrees up or down to move my radius vector, and I can get to that point. So what we got to be able to do is go between one form and the other form. So let's look at how we would do that. Now, what you guys got to do with me right now, don't really worry about why we're doing this. Don't worry about that at all. Just understand what I'm doing. And like I said before, if you did that lab and went through it and really understood it, then this is like a review. You've seen it. But if you're a little confused or you're wondering, well, I need to see it. Well, we're doing it now. Hopefully it becomes crystal clear. The reason why we're doing it will become completely evident when I apply this to circuits. Don't worry about why we're doing this. Just worry about what we're doing right now and make sure you understand it. So if let me draw this again. So let's say I have my complex plane, and my complex number is right there, and this is A, and that's B. Well, if that's the case, If I wanted to, then what I can do, if I go over A units like that, and then I go up B units, you'll notice if I do this, then that makes a right triangle, which is nice because we know all about right triangles. And if this makes a right triangle, here's my right angle, and I know this right here to be A, and I know that right there to be B. But what I don't know is, I'll put that in red, I don't know this hypotenuse right there. That would be my radius vector, wouldn't it? And I don't know this angle right there. That's my phase angle. I don't know that. So given this and this, how could I get the radius vector of the hypotenuse and that angle right there? Well, that's pretty easy. You remember, I have a right triangle. Now let me do this in another color. Your Pythagorean theorem, I have a right triangle. I know that leg and that leg. I want to get this one. And I guess I should be using, normally when you do right triangle math, they use lowercase. I'm going to follow what they do in trig. They use uppercase letters for angles and lowercase for the legs of the triangle and the sides. And they use, sometimes they'll use a Greek letter for that. So I really should say, to review this is A, B, C, lowercase. And you'll remember that C squared is equal to A squared plus B squared. And if I want C, I can take the square root of both sides, and then C would equal that. So, given this A and this JB, and I want to know the radius vector R, the magnitude of R. So I'm just putting in an absolute value sign because you can't have a negative radius vector. You can't have a negative radius of a circle. It's going to equal A squared plus B squared square rooted. That'll give me the length of the radius vector. And then all you got to do is figure out how far up or down in degrees to move that radius vector to get to that complex number. Well, what do we know? We know this and this. And remember from your trig, when you took that, if this is the angle I'm talking about, if that's the angle, this is the side opposite the angle, and then this is the side adjacent to the angle. And remember those trig functions, the sine, cosine, and tangent? Well, the tangent of an angle is equal to the opposite side over the adjacent side, is what they taught you in math. So the tangent of this would equal B, the opposite side, over A, the adjacent side. And so the tangent of that angle is B over A, but we don't want to know the tangent of the angle. We want to know the actual angle. So if you remember that from trig, how you get the actual angle, well, you got to undo the tangent. And that's called the arc tangent or inverse tangent. And they usually show that like this. Let me put it right here. So if I want to get that angle is going to equal the inverse tangent, like that, of B over A. Sometimes they call that the arc tangent, which I like a little better, of B over A. That's an older name right there. So you usually see it that way. So I got, I don't know if it's a glare. I guess you can see it if I write it. So I'm going to use the inverse tangent function of B over A to get this angle and to get that radius vector. Now what we just did, we knew A and B. So if I gave you, say I gave you a complex number 2 plus J3, this is the A and that's the B. That's rectangular form. We want to get the radius vector and the angle, that would be polar form. So by doing this, I can get the radius vector or the magnitude, and by doing that, I can get the angle, and so I can convert rectangular form to polar form by doing this right here. So that's just a little trig review. So if I'm in rectangular form, it's easy to go to polar form by using Pythagorean theorem. and the inverse tangent. Okay, well, what if I was already in polar form and I want to go to rectangular form? How would I do that? Well, let's look at that one. So let's say that they gave me, draw my coordinate system again. They gave me, here's my point, there's my complex number, here's my real axis, here's my imaginary axis, and they gave me the point, but they gave me, what they gave me, let me drop a perpendicular line down, and then one over like that. Okay, so what they gave me was, they gave me this distance right there, that's my radius vector. They gave me r, and then they gave me this angle right here, theta. So let me pull this off over here so I can draw it so it's clear. If you look, I can do this. That makes a right triangle. So my right triangle is right here. It consists of this side we don't know, that's side B. This side which we don't know, that's side A. And then this side which we do know, that's R. That's my radius vector. So let me color in what we don't know. We don't know A, so I'll make that red. We don't know B, so I'll make that red. We do know R, that's the radius vector. And we do know this angle right here, theta. So if they gave us R and theta, how would I get A and B? Well, again, that's just some simple trig stuff that you learn. So if I know the hypotenuse and an angle, how do I get a side? Well, if you remember, let me go ahead and name this again. This side right here is the opposite side. This side right here is the adjacent side. And you might remember from your trig class that the other part, we did tangent already. We always use the tangent when we want to get our angles. But when I want to get these sides, I'm going to use the sine and the cosine. So the cosine of an angle, here's what you learned in trig. The cosine of an angle is equal to the adjacent side over the hypotenuse. And the sine of an angle is equal to the opposite side over the hypotenuse. That's what they taught you in your trig class. And so if you think about it, we know the adjacent side. I mean, we want to know the adjacent side. We don't know it. That's what we're looking for. We're looking for A. So I'm going to erase this and put the A there and keep it in red. The red is what we're looking for. So we don't know that, but we do know this. We know the radius vector. That's my hypotenuse. And we also know that angle right there. So we know the angle. So the only unknown I have is A. So how would I get A? Well, what I have to do is multiply both sides of this, of course, by R. I multiply this by R and this by R, and that goes away. And then what I get is that A is going to equal R cosine theta. And I have the same logic down here. I don't want to go through the whole thing, but for the opposite side down here goes with the sine. I can put a B down there over the hypotenuse, and that would be an R. No R. We also know that angle, so I'll make that black. And I can do the same thing that I did here. I can multiply both sides by R. And if I do that, what I get is I get B equals R sine theta. And so what I have, guys, is this. Just to sum up, the way I show this, if I want to convert a number from rectangular to polar, I'll show it like that. I'll put these two colons and then I'll do my math. If I want to go from polar to rectangular, I'll show it like that, put two colons and then do my math. So here, we know rectangular, we want to find R and the theta. So this takes me right here from rectangular to polar form. This set of equations right here goes from rectangular to polar, or I can do the other way. Here I know r and I know the angle, and I want to find the real part and the imaginary part. So this takes me from polar to rectangular. You want to remember formulas. They kind of be pretty important. But again, if you did the lab, you did all of this before, and hopefully this just kind of makes it a little bit more real to you. You can kind of see a little bit better. Sometimes when you read something and somebody talks about it in a different way than what you read it, it makes it make a little bit more sense. And when I apply this to circuits, it'll make perfect sense. You'll say, okay, I get it. So I'm not even worried about that. It'll be crystal clear. So what I want to do is, let me make sure I covered, I don't know if you have the topic sheet out. But first, let me slow down. Anybody have any questions so far? I'm just rambling and going. Anybody have any questions about what we talked about so far? Okay, so let me read I don't know if you have the topic sheet, but I was able to print one out. Sometimes my printer works, sometimes it doesn't. So I was lucky today. So complex numbers. The first thing says, why do we use complex numbers in AC? Why do we use complex numbers in AC? The reason we use or need complex numbers in AC is because unlike other areas like banking or finance, we have numbers, or we work with numbers that don't have a phase of 0 or 180. Any number that has a phase of 0 or 180 can be dealt with on the regular number line, and you never even have to talk about phase. You talk about the plus sign and the minus sign in front of a number, and you're good to go. But in AC, we have special numbers that have phase of 90 and negative 90, so we need an imaginary number for that. And we also have numbers that have phase anywhere in the plane, the complex plane. So we got to have a special number for that called a complex number. That's the reason why. We have these quantities in nature that fit that schema, whatever you want to call it. What is a complex number is the next question. Well, I gave you two ways to think about a complex number. Way number one, a complex number is a number that consists of a real part and the imaginary part, and hence the name complex, meaning it has not necessarily hard, but it has pieces to it. So a complex number is a number that has a real part and an imaginary part. Or you can say a complex number is a point in the complex plane, and I showed you both of those on the board. Then it says talk about the complex plane. Well, I drew that for you. I have real numbers here, and I have imaginary numbers here. That's the complex plane. D, if you look at 1D, it says J is a rotational operator. What's that mean? I didn't show you that. I mean, that doesn't really have an application for what we're doing, but I can show you anyway. I mean, it's part of math, so I'll show you, and then you can forget about it if you want. So they call the J operator a rotational operator. But to understand it, so guys, remember this. If you don't have this written down, it's on the topic sheet, but write this if you have paper. We'll come back. We're going to do some practice problems. I want you to write this down so I can erase it. You'll have it there in front of you. All right, so what do they mean by a rotational operator? Well, here's what they mean. And I don't know what this is good for. I mean, it's kind of neat, but I don't know what you would use it for. So say we have a unit circle. A unit circle, we go out 1 unit, 1 unit, 1 unit, 1 unit. And I don't know if let me see if I can draw this circle. Let me make it a different color. I'm not good at doing this freehand stuff, so see how this turns out. That's not too bad. So I got a unit circle. And this, of course, is my real numbers. These are my imaginary numbers. So over here, that plus sign means everything from the origin over has a phase of 0. The minus sign means everything from the origin over there has a phase of 180. The plus J here means everything from here to there has a phase of 90. And the minus J here means everything from there down has a phase of minus 90 or 270. Now what you can do is take this radius vector and you can point it, start it over here, call that the standard position, just to call it something. Now what you got to remember is, now remember in math, what we're calling J, in math they call I. So if you remember what I showed you, call that I. And so if you have 3I, that really is a square root of minus 1. So I equals the square root of minus 1. Well, if I square this, then that's like squaring this. If I square a square root, that undoes. Is that right? I don't know if it's undone or undoes or undid, whatever. It will undo. It'll undo the square root. So I squared is equal to minus 1, right? Well, remember, we're using J. So for us, J squared is equal to minus 1. And the way you do the rotation is this. Every time you move around a quarter circle or 90 degrees, that's one factor of J. So what I'm saying is this. If I start right here, then that rotation, let me show you what I mean by rotation. So I got this radius vector. I'm going to rotate it around. And by the way, anytime we do a rotation, it will always be counterclockwise. And, I don't know if I mentioned that, but I'll mention it again when we talk about phasors. Hopefully we get to that today. So I rotate counterclockwise, and if I go from here to here, that's one rotation of J. So there's one factor of J. So as I rotate around, here's how you write it. This would just be this rotation from here to here, that's J. And if I go again, that's another factor of J. So this is J times J. Every time I rotate a quarter of a circle, it gives me another factor of J. So this is J times J times J. If I go all the way around, this is J times J times J times J. All right, so this is just that. It's just J. But J times J is J squared, and J squared is equal to negative 1, which is what we get right here in the unit circle. If I come down to here, I got J times J times J. Well, that's J times J is J squared. So this is J squared times J. But that J squared, remember, is negative 1. So that's a negative sign. It gives me the minus J right there. If I come up here again, I get 4 factors of J. Every time I go a quarter circle, I'll multiply by J. So this is J times J times J times J. So this right here is J squared. This right here is J squared. But that J squared is equal to minus 1. And that J squared is equal to minus 1. And minus 1 times the minus 1 is a positive 1, which is what you get right there. So again, I don't even know why I put this on here. I probably was reading back in the 90s and said, that's kind of interesting that J is a rotational operator. But I don't know what the heck that's good for, other than to show people how smart you are. I don't think we can use that for anything. Well, we do use this idea. You'll see that probably today, that J squared is negative 1. We do use that. But the rest of the stuff, I don't think I've ever used it before, other than to show this. So that's D. Now, on 1E, it says rectangular form. It shows you how to express a complex number in rectangular form, and I'll just put it on the board. We've already done this, but I'll do it again. So I can express a complex number like this. And that would be rectangular form. Or I can express it as a radius vector and some phase angle. and that would be polar form. Okay, so we can show two ways to represent a complex number. All right, now I'm looking at this sheet. I forgot one thing. If you got the sheet, I'm looking at 1F, and I'm going to read it. It says polar form, and what they have for polar form is something like this, but they use a Z. Let me erase this. All right. Here, let me write this on the board. I'm going to try to explain it. This will make sense, I hope. So I'm looking at 1F. So at the bottom of 1F, they have this minus C equals minus. Now on here they have a Z. I'm going to use an R because we started with R. So that's my radius vector at some angle. And it says equal to R angle theta plus 180 degrees. So look at that for a second. Look at it. I'm going to explain it, but I want you to look at it. Study it for a minute and see if you can understand what it's saying. If you look at that, you'll notice that, okay, here's the thing. Where did we get that R from? Let me show you how we got the R. To get the R, I gave you this complex plane. This is real. That's imaginary, right? See that? Here's our complex number represented as a point. We know one way to get to it is to go over A units and up or down JB units. But the other way would be to find the arc. You know, that's what I said. You got a compass. So find the arc and mark that arc with like that. So I mark the arc for this so I can find the circle that cuts through that point. And then I know if I have my start here and go over to here, that's the radius of the circle. So we call that a radius vector. So I already know that if I'm touching that line, I'm touching the line that goes through that point. So at that point, all you got to do is tell me how many degrees up to move that radius vector, and I'll be pointing dead at that point. But the point is that this thing right here is the radius of a circle. And you're not allowed to have a negative radius. Think about that. What does that mean to have a negative radius of a circle? It's impossible. You're not allowed to have a negative radius. So that's what we have here. If I have a minus complex number, the way I show that is I got a negative radius, and that doesn't make sense to have a negative radius. So how do you fix that? Well, this says to take the angle theta and add 180 to it. And then you can get rid of the negative sign. So let me show you why that works. Here's why it works. You got to know a little bit about vectors. And if you don't, this should make sense to you. A vector is just a quantity that has direction and magnitude. So I usually draw a vector with an arrow. So a vector A, I might draw like this. That's vector A. So A has a certain length, that's vector A. And usually they show a vector like that. That vector has a certain length, and also if I put it on the coordinate system, it also has a certain direction, which I can show with that angle right there. So that's vector A. If that's vector A, what would this look like? Vector 2A. Well, it'll look just like this. I got to draw it exactly the same angle, but it'll be twice as long as that. So it'll be twice as long. So I can scale the vector. If I multiply it, it gets longer. If I multiply by a fraction, it gets shorter. But that angle never changes. But what would this look like? If that's vector A, then where's negative A? Where's vector negative A? Negative A is always the mirror image. It's the mirror image. So what I mean by that is, imagine I hold a mirror right here. If that's A, if I hold a mirror right there and I look into the mirror, what I would see in the mirror is another vector going in the mirror like this. So if this right here is vector A, then this is negative A. That's the negative of A. If it was up like this, the negative A would be down like that. The negative of a vector is just, it's 180 degrees away from it. So that's how this is going to help us. Let's say I have a complex number that's negative, that I'm not allowed to have. So let's say I got this. Let me put it, I'll just put it right here. So here's my complex number. Let me put it in the first quadrant. It doesn't really matter which quadrant it's in, but let me just put it here. So let's say this is my number right here. And that number is, I want to use these symbols. We'll use real numbers. Let's say it's -3 angle, I don't know, what, 20 degrees? Like that. Actually, let me not do that because we're going to do an example. Let me try to stick with just these symbols right here. So what they're saying is that this right here is minus r angle theta. That complex number in polar form is a negative radius vector, which we're not allowed to have. So it's sticking up like this, right? Well, if this is negative r, if this vector right here represents negative r, this is negative r, that represents the negative r, and this angle right here, that's theta, that's this. If this represents negative r, where's positive r? Positive r is over here. This is negative r, positive r is the mirror image, is over here. So what this is saying is that if you just get rid of the negative sign, write it as positive r, but then you have to take this angle and you got to add 180 to it. So if I take this angle and add 180 to it, what it's going to do is take that positive number, it's going to flip it up right on top of that negative radius vector. So I don't know if you can see that, if that makes sense. It makes perfect sense to me in the picture. But here's all this is saying is, if they give you a complex number in polar form, negative sign in front of it, you want to get rid of the negative sign because you're not allowed to express it that way, all you got to do is drop the negative sign and add 180 to whatever the degrees are. And then you can write it as a positive number. That's what this is saying. I was trying to explain why, and probably some of you will get it, some you won't. But it's okay. If you don't understand the theory, as long as you understand what this is telling you to do, you're in good shape. So that was part one of the topic sheet. Now part two is conversions between forms. And I already put the formulas up there. He shows you how to go from polar form to rectangular and from rectangular to polar. So then after that, he gives us some operations with complex numbers. So let's take a break and let's go ahead and do some calculations. So if you have a sheet, take it out. And I want to do problem number 1, 2, and 3 on the sheet. Now, if you don't have the sheet, I'll put it on the board. But I do want you to work along with me, even if you did the lab packet. I think it'll be a good review for you. So let's do some practice problems. All right, so on the set of practice problems, it says determine the this is pretty simple. It says determine the quadrant for each point and sketch the complex number as a point and a radius vector. That's really a little too simple. Let me put it up here and we'll go ahead and do it real quick. So they got 3 plus J4. They got 0 minus J6 they got minus 10, minus J20. And what they want, all this is doing is making you think about the quadrants. You got to remember how the quadrants are. So this is like review. So if you remember from your algebra class, this is plus plus, right? So like this is plus plus, so that's quadrant 1. This is minus plus, this is minus minus, and this is plus minus. So if you look at the signs here, you can tell which quadrant you're in, and that's all they're saying they want you to do. So you go ahead and do that. Like we'll do the first one together. They want you to make the coordinate system. What quadrant is this in? Well, it's in quadrant 1 because they're both positive. And if you can put the dot, you don't have to measure or draw a scale, but you kind of go over 3 and up 4. It might be over like that. So there's the dot. There's my complex number. They want you to show it as a point and as a radius vector. So then all you would do is get a different color marker and then just draw a little arrow out to it. And that's what they want you to do for the other ones. So you go ahead and do that for this one, and that one. I thought I had 4 of them. Do I have 3 or 4? I just got 3. Okay, so you do the next 2. Just basically graph it. That's all they want you to do is graph it. So that'll take you about 2 seconds. So go ahead and do that. If you graph this one, I'll make my coordinate system. And this is just 0, J6. So J minus J6 is like down here somewhere. So there's my point, and there's my radius vector. So that's not in the quadrant. That's right on the axis, the negative J axis. And then if I'm over here, I'm in minus minus. So that's quadrant 3. I go over 10 down 20. So it might be down here like that, just to guess. And so there's my point. And if I show it as a radius vector, that's it. So that's all they want you to do for that. That's pretty simple. But let's see what else they want you to do. So then he says, sketch the following complex numbers. Sketch the following complex numbers in polar form. Again, this is really simple. It's almost so simple as stupid. But they just want to get used to kind of thinking where these angles are. So I guess it's not really stupid. Let me put it on the board. You can see what I'm saying. They just want you to make a quick sketch like we did, but they give it to you in polar form. So for the first one, all right, so for the first one, they give you 5 at an angle of 30. And then they give you 7 angle minus 20, or 120. And they give you minus 4.2 angle 60. All right, so all I want you to do is graph it. So we'll do the first one together. So you make the coordinate system. You got to say 30 degrees. Well, where's 30 degrees? That's like, well, if I go all the way in the middle, it's like 45. So 30 is probably like right there. So you put a point, and just like before, you draw your radius vector out to us, like that. So this is kind of a guesstimate. It doesn't have to be exact. So I want you to graph that one and that one. So I'll pause for a second, let you do those 2. Graph them. If you graph this one, that's a minus sign, so you're going to go this way, clockwise. And so if I rotate the vector from here to here, that's 90, and probably another 20 degrees is like maybe right there. So I'm going to say that that radius vector is right there. It's just a guess. But you can see that you're in quadrant 3. Now, this one, we got a problem because I'm not allowed to have this right here. There's no such thing as a negative radius vector. So I got to express this as a positive number. So the way you do that, what I said was, if I have a negative sign out front, you can erase the negative sign if you add 180 to the degrees. So I can write this as 4.2. I can get rid of that negative sign if I take the 60 degrees and add to it 180 degrees, like that. This will be 4.2. What is that, 20? Is that 240? I think it's 240. Did I do it right? Yeah, I think it's 240. So if I write it like that, then I'm good to go. Now I just applied that rule that I tried to explain. Get rid of that by adding 180 to that, and then these are equivalent. So this is the way I want to write it. Now I can do, I can take this 360 minus 240. I can use a smaller angle if I want to, which is probably a good idea. But since I add, it was easier for me to add and get to 240. But if I want to go ahead and graph it, I'll just graph it down here. That's 90, 180, 270. So 240 is probably like maybe over there somewhere, like that. So I can draw my radius vector down like that. So this is a good exercise in how to change that negative radius to a positive radius by adding the 180 to it. Okay, so that was pretty easy stuff, guys. Hopefully that's nothing to write home to mom about. This is pretty simple. Now we'll do some conversions. We're going to use those formulas to convert from rectangular to polar. So I'm going to need your help because I don't have a calculator. So I'll put these on the board. You get your calculator out, and we'll convert these to the opposite form. It wants to convert it to the opposite form. I really want to clean this board. This board is terrible. I hate to use up big time cleaning it, but it's getting on my nerves. Let me put it up here. So what I'm going to do is I'll put these up here, and I think while you guys are working on this, I'm going to go ahead and try to clean the board. So the first one is 3 plus J4. And they give you minus 6 plus J3. And they give you minus 2 minus J4. And they give you 4 minus J3. And they give you 10 angle 45 degrees. Okay? Now, before you start working on this, I got to explain something to you. So everybody, if you're doing something else, just for now, watch what I'm about to do. Your calculator has an issue, has a problem, and I'm going to show you what it is. All right, so let me see if I can explain it like this. You know the sign in each quadrant. For example, you know minus, you know that's plus, plus. You know this is minus, plus. You know this is minus, minus. And you know this is plus, minus. Everybody knows that. Well, these quadrants, let me number these. This is quadrant 1, 2, 3, 4. So they're my 4 quadrants. If you're doing math in quadrant 1, okay, if you're doing math in quadrant 1, so if both of your numbers are positive, you're in quadrant 1. When you convert this, see I'm giving this number in rectangular form. I want to convert it to polar. Okay, so when I convert to polar, what I got to do to convert to polar, I got to take this number A and square it plus this number B and square it. You gotta take the square root of it. That's how I get R. But to get the angle, because polar is the R and the angle. So this gives me the R, but to get that angle, that's where the problem is. Watch how I get the angle. To get the angle, what I do is I take the inverse tangent of A over B. I'm sorry, B over A. But you can see if this is B and that's A, then my inverse tangent is a positive number over a positive number. And I'll get some angle over here if you did that. Well, the problem is you get exactly the same thing if you're quadrant 3. If I'm in quadrant 3 and my complex number is over here, then if I take the inverse tangent in quadrant 3, I got the inverse tangent of a negative over a negative. Well, a negative divided by a negative is a positive, and the positive divided by a positive is a positive. So this is going to give you an angle in quadrant 1, but you know you're in quadrant 3. So what you got to do, given a radius vector in quadrant 3, since you know the calculator is going to give you the angle as if you were in quadrant 1, you got to add 180 to it. So when we give you the quadrant 1 angle, you got to flip it back around and add 180 to it. So hopefully that makes sense. You got a problem between these two. The calculator will give you the right answer here, but if you're here, it'll give you a first quadrant angle because a positive divided by a positive gives you a positive, and a negative divided by a negative gives you a positive. So it doesn't know, all it sees is a positive number there. It doesn't know if you're in quadrant 1 or quadrant 3, so it assumes you're in quadrant 1. So if you know you're in quadrant 3, you take the answer from quadrant 1 and add 180 to it, and it'll flip it around. Well, that's the same down here. If I'm down here in quadrant 4, and I want to do this. This is B, and that's A. So I want to find that angle. The angle is going to be the inverse tangent of B, which is negative, divided by A, which is positive. So if I take a negative divided by a positive, I get a negative. But the problem is you get exactly the same thing in quadrant 2. If I do quadrant 2, the inverse tangent of this is A and this is B. So this will be the inverse tangent of B, which is positive, divided by A, which is negative. It doesn't matter if you have a negative divided by a positive or a positive divided by a negative. Inside of here, I'm going to get a negative number for both of these. So if you're here, you're going to think you're in quadrant 4. So here's the rule. When you start with these numbers, first check to see what quadrant you're in. If you're in quadrant 1 or quadrant 4, the answer you get in the calculator will be correct. If you're in quadrant 1 or quadrant 4, you check the signs. Plus, plus, that's quadrant 1. Minus, plus, that's quadrant 2. You got to check to see which quadrant you're in. If you're in quadrant 1 or quadrant 4, the answer you get on your calculator for the angle is correct. If you're in quadrant 2 or quadrant 3, you got to add 180 to it because it's going to think you're somewhere else. So if you can remember that, you should go. Now go ahead and convert these over. We'll do the first one together. Then I want you to convert the other ones over to the opposite form. So we'll do the first one together. And then while you guys are doing the rest, I want to clean this board off because it's just really dirty. So if we do the first one together, I want to take 3 plus J4 and convert that from rectangular to polar. So if I didn't want to show the math, I could just show that right there. But I'm going to go ahead and work it out. So in polar, we got to find the magnitude of the radius vector, which is equal to A squared plus B squared square rooted. And we got to get the angle, theta, which is equal to the inverse tangent of B over A. So we got to do that. Well, here I got A is 3. So I got 3 squared plus B is 4. 4 squared square rooted. That gives me a 9 plus 16, which is 25. So the square root of that will be 5. And I got to get the angle. The angle is going to be the inverse tangent of B over A. So 4 over 3. So I got a 4 and I got a 3. Now I need your help on this. Make sure your calculator is in degrees. This is the only time you're going to have it. Well, that's not true. Keep it in degrees. The only time you put it in radians is when you have a sine, that thing that I showed you last time. But make sure you're in degrees, and somebody take the first tangent of 4 over 3 and tell me what you got. Do the calculation for me.
53.13.
53.13 degrees. All right. So there's an example of how you do that. So I'm going to clean the board, and while I'm doing that, you guys do the other. There's 4 more problems here, and then I'll check them with you. We'll check to make sure you did them right. So on your scrap paper, go ahead and work them out. And by the time I'm done cleaning the board, it'll be time to go over them. But I gotta get this board clean because it's really driving me crazy. So, matter of fact, let me just erase the whole thing, and I'll rewrite it once I clean it. All right. So let's go ahead and look at this together. So the first thing you got to do is check the quadrant. If you're in quadrant 1 or 4, you're okay. If you're in quadrant 2 or 3, you got to add 180 to the degrees when you do your inverse tangent. Quadrant is this in? This is in quadrant 2. So when I do my angle, I got to add 180 to it. So I'm going to get my radius vector length. I'm taking minus 6 squared plus 3 squared, square root it. Somebody tell me what you got for that. What'd you get for that? The square root is 36 plus 9. What is that? I can't think right now because I'm hot and bothered. But what'd you get for this?
6.7.
6 ones, what is it?
6.7.
Okay. And the angle, so the angle is going to be the inverse tangent. Now, even though I know when I square this, I'm going to get a positive 6. So you might say, well, why are you writing a negative sign when it's just going to go away? Well, I got to use it over here. So that's why I write the negative sign so I remember. This is going to be the inverse tangent of 3 over minus 6, or the inverse tangent of minus 1/2. What do you do what do you get when you do this? What's the inverse tangent of negative 0.5? What is that?
26.
26.56 degrees. So look at this. From the problem, I can see that this is negative and that's positive. From the problem, I can see I'm in quadrant 2, but this is telling me I'm in quadrant what? Am I in quadrant 2? Is this positive or negative? This should be negative, isn't it? It's got to be negative. That's a negative angle, negative 26.
Yes.
Okay. So that's telling me I'm in quadrant 4. Negative 26 is down here. And I know I'm up there. So you got to add 180 to this. So add 180 minus 26.56 is what? What is that?
$153, $144.
All right. So that's an example. If you're in quadrant 2 or 3, you got to do what I just did. You got to add 180 to your answer when you do the inverse tangent. So you got to remember that, else it's going to screw you up in your calculations. So everybody have any questions over what we did? Let's go ahead and finish. All right. For the next one, which quadrant are we in? We're in quadrant 3. So the calculator is going to give us an answer in quadrant 1. So we're going to have to add 180 to it. So that's going to give us the wrong answer. So let's find the length of the radius vector. Minus 2 squared minus 4 squared square root. Let me know what you got for that. And then we got to do the inverse tangent of minus 4 over minus 2. Let me know what you got for that. So what'd you get for this?
$4.47.
12.47? Like that? Is that what you got?
No, I say 4.47.
All right. And what about here? The inverse tangent of 2.
53.4.
53.4.
63.4.
All right. So we know we're in now. We're at 63 degrees. 63 degrees. We know right here, minus minus. We know we're over here. But this is giving me an angle in the first quadrant. So what I got to do is take this and add 180 to it. So if I add 180 to that, it'll be what? Should be able to do it in my head. Is it subtract 20? Is it? I don't know. You do it for me. I can't do it in my head.
It's
Not right now.
240. It's 243.43.
All right. So there's my angle. All right. Now you could subtract that from 360 and use a smaller angle written as a negative, but this will work if you can see what we just did here. So for both of these, notice I had to add 180 because I was in those quadrants. Quadrant 2, quadrant 3 is going to give you the wrong answer for the angle. You got to add 180 to it. Now this one, I should be okay because I'm in quadrant 4. So it should be okay. So let's do that one real quick. Get rid of these. So I got to get my radius vector. I got 4 squared plus negative 3 squared, square rooted. And then for the angle, I get the inverse tangent of minus 3 over 4. 16 and 9, that's going to be 5, right? Yeah, that's 5. Angle, what's that angle?
Minus 36.86.
Like that?
86.86.
86?
No, 0.86.
Yeah, your mic cuts off, so I can't, the first part or whatever you say.
Yeah,
It's
I
30.
said minus 36.86.
Like that?
Yes.
Okay, everybody okay with that? Okay, so that one worked out okay. Now this one, it wants to go the other way. They give it to us in rectangular, polar, it wants to go to rectangular. So that's easy. So remember, in rectangular, I got the real part and I got the imaginary part. I get the real part by doing r cosine the angle. I get the imaginary part by doing r sine of the angle. So I got r here is 10. I got 10 cosine 45 degrees. And I got 10 sine 45 degrees. And this one might look a little strange. You might remember from the trig class that the sine of 45 and the cosine of 45 are both equal. The sine of 45 and cosine of 45 is 0.707. If I multiply that by 10, I get 7.07 for that one, and I get 7.07 for that one. But again, that's just the same because the cosine and sine are equal at 45 degrees. So if I write that like this, I would write it like 7.07 plus j 7.07, and that would be my conversion. You should be able to do that like really, really, really fast. So you want to get used to working with these complex numbers. You got to be able to go from one form to the other form really fast. And the reason is, here's why. When you add or subtract, if you add or subtract complex numbers, then the best form to be in is rectangular form. If you multiply or divide complex numbers, the best form to be in is polar form. Now you can do it in either way, but it's faster to add and subtract in rectangle. Now the only time that's not true is if the phase angles are the same. I'm saying if I had 5 at an angle of 30 degrees plus 10 at an angle of 30 degrees, and I can just add these two, I get 15 at an angle of 30 degrees. But that only works because my angles are the same. Usually these will be different. So if these are different, it's hard to add that way. What you got to do is put it in rectangular form and do your addition or subtraction. So we're going to practice doing some operations with complex numbers. And just remember, if I'm adding or subtracting, I do that in rectangular form. If I'm multiplying and dividing, I'm going to do it in polar form. So when we apply this to a circuit, anytime you add or subtract numbers, you got to have it in rectangular form. Anytime you do a multiplication or division, you got to have it in polar form. So what I usually do in these circuits is when I express it both ways, so I have it there. I don't have to do any conversion. It's right there. But you'll see that when we get to that. We won't get to that today, but you'll see it. So let's play around and do some conversions. And now if you have the sheet, I am on problem number 4. So number 4 gives you two complex numbers. Complex number 1 is 2 plus J4. Complex number 2 is 3 plus J1. And they want you to find C1 plus C2. And they want you to find C1 minus C2. All right, so how do you add complex numbers? Well, adding complex numbers is super easy if you're in rectangular form. All you do is you add the real part to the real part and the imaginary part to the imaginary part. So for this one, I get 2 plus J4, 3 plus J1. I'm going to add the real part to the real part, so I'll get 5 plus J5, and I'm done. So addition is really simple. Now subtraction is it's not hard, but you got to do an extra step. You guys know that I can do this. I can take 7 minus 4. Everybody knows that's 3. But what you can also do is take 7 plus the opposite of 4 and get 3. So if I add the opposite, I'm really subtracting. So that's what we got to do here. If I want to subtract complex numbers, I'm going to add the opposite. I want to take C1 and take C2 away from it. So I got C1 is 2 plus J4. Now here's C2, but what I want is to add the opposite. I need the negative of C2. So to get the negative of C2, whatever sign I have, I just flip the signs. I got a plus, so I change it to minus minus. If I had a plus minus, I would change it to minus plus. Whatever the sign is, you flip it. So if this is C2, negative C2, it's going to be minus 3 minus J1. So I'm going to add that to C1. So if I add this, I get a negative 1. I get a positive J3, and that's the difference between the two. So when you do a subtraction, just add the negative of the thing that you want to subtract. So that's that one. So addition and subtraction is pretty easy. Now for the next one, they want you to multiply and divide. So when you do that, you want to be in polar form. So let me show you that. So they give you C1, (5 angle 20), and C2 10 angle 30. And they want you to find C2 times C1. They want you to find C2 over C1. And they want you to find C1 over C2. So they want you to multiply and they want you to divide. Well, if you're in polar form, multiplication is easy because all you do, you multiply the magnitudes and you add the angles. Multiply the magnitudes and add the angles. So for this one, I got C2, which is 10 angle 30. I'm going to multiply that by C1, which is 5 angle 20. And what you do, when you do this, you multiply the magnitudes. When you multiply this and this, I get 50. And this, you add the angles. You add. I get 50 angle 50. So that's really easy if you have it in polar form. Now, think about it. If when you multiply the magnitudes and add the angles, it will make sense that when you divide the magnitudes, subtract the angles. So that's exactly what you do. So go ahead and do this one and that one. You divide the magnitudes and subtract the angles when you divide. So you go ahead and do the other two. All right, so I got C2 over C1. So C2 is 10 30 divided by 5 angle 20. And so I'm going to divide the magnitudes. I'll get 2. I'm going to subtract the angles. I got 30 minus 20, 10 degrees. So that's how you divide. For this one, C1 over C2, if I flip it over, I got 5 angle 20 divided by 10 angle 30. I divide these. When I divide these, I get 0.5 angle. If I take 20, subtract 30, I get a negative 10. So there's my division. So the rule is, remember, when you add or subtract complex numbers, you want to be in rectangular form. When you multiply or divide complex numbers, you want to be in polar form. Now, having said that, if you look at number 6, they give us two complex numbers in rectangular form, and they want you to multiply them in rectangular form to see how much work it is. They don't want you to convert to polar. They want you to multiply it in rectangular form. So let's go ahead and do that. All right, so they give us 2 plus J3. They want you to multiply that by 6 plus J8. Now you could, you could convert both these to polar, multiply them, and then convert it back to rectangular. Usually the way they give you the problem is how you want to express it. So since they're expressing in rectangular, you want to show your answer in rectangular. So you could convert both these to polar, multiply them, and convert it back to rectangular. But they want you to multiply it as shown. So how would you do that? Well, you would do this. You can use your FOIL method. Remember that FOIL thing you learned in algebra? I don't use FOIL. I just make sure every term over here is multiplied by every term over there. So you go ahead and do that. I'll pause for a second and let you do that. And then we'll do it together. Okay, so if you're doing this, and you might have do a little differently, but if I multiply this times that, I think that's 12. You might have to help me with my arithmetic. Multiply this times that, that's plus J16. Multiply this times that, plus J18, and multiply this times that. Now, when you multiply that, you got to be careful because what you have is J3 times J8. So you got to multiply these, and you got to multiply those. When you multiply those, 3 times 8, you get 24, right? But when you multiply J times J, remember J times J is J squared, but J squared is equal to a minus 1. So you really have minus 1 times 24, which makes that a negative 24. So what do I have here? I got, if I add this, I get a minus 12, and 6 and 8 is what? That's, what is that? 12, 14. Is it 34? I think it's plus J 34. Did I do my arithmetic right? Is that what you got or not? 10, 12, 4. I think that's right. Or is it 24? 20, I think it's 34. Is that what you guys got?
I got 34. I got 34. Yep.
I feel like I'm talking in a void. Is anybody still out there? All right. All right. So that's it for this, but we're not done yet. There's another sheet. We're kind of behind, so I really do want to go through this other sheet on phasors. But I've been talking for almost 2 hours, and I'm kind of tired. So I do want to cover this sheet, but I want to take a break. I hate to have this dead time on the camera. I want to take like a 5-minute break and come back. And then there was a sheet on phasors I want to talk about. We'll go over that, and then we'll call it a day. This shouldn't be too long. This will go pretty quick because, this will go pretty quick. So let's take a break, about 5 minutes. I'll just have to have dead time on the camera. When I pause it, I have to start the video all over again, and I end up with 2 videos. So I'm just going to let it run for about 5 minutes. And I'll come back in about 5 minutes. So if you guys want to take a bathroom break, or you've probably been doing it already because I can't tell when you leave your computer, but I got to take a break for a minute. So go ahead and come back in about 5 minutes, and we'll talk about phasors, and we'll finish up for today. I'll be back. Okay. All right. So a couple people hanging in there. That's good. Got about 1 minute left, and then we'll continue. I think I have this scheduled to go to 4:20. Hopefully we can get done quicker than that. All right. So if you have the printout on phasors, take that out. If not, I'm just going to read from it. I want to define a phasor, and then I want to, we've got a few practice problems to do here that we'll go through. So I'll just read from the sheet. A phasor is a rotating arrow fixed to the origin. We already talked about that. I drew a phasor when we looked at that generator. We put a arrow on the generator coil, and then I drew a set of axes, and I put the arrow on the axis, and we call it a phasor. So this phasor rotates, and they always rotate counterclockwise. So what changes is this angle here. The angle theta changes as it goes around. So a phasor. So back to the sheet. A phasor is a rotating arrow fixed at the origin. The projection of the height on the y-axis at any instance in time will give the corresponding instantaneous value of a sinusoidal waveform. That's exactly what I showed you. If you remember, I won't go through the whole thing, but what I said was we put a light source right here. So I got maybe a flashlight, and I look at the projection of the shadow of the phasor as it moves around 360 degrees. What it traces out, and I'll just do it real quick. When it's at 0 degrees, we had a dot, and then we had something that looked like this. That's in quadrant 1. In quadrant 4, the shadow got smaller until it was a dot again. When I get down here in quadrant 3, it starts to grow in the opposite direction. And in quadrant 4, it starts to shrink until I get back to a dot. And that's the sine wave. So the height of the shadow gives the instantaneous value. At this time, the instantaneous value is there. It gives you the instantaneous value at each time, the height of the shadow of the phasor. So we kind of went over that, but we're going to do something called phasor algebra. Phasor algebra. So the algebra uses this phasor idea. So phasor algebra, I'm just reading from the sheet. Phasor algebra for sinusoidal quantities is applicable only for waveforms having the same frequency. You got to make sure you understand that. If I'm doing this math called phasor algebra, I got to make sure the frequencies are the same. How do you know if the frequencies are the same? Well, it's pretty easy. Remember our AC waveform. Suppose I have 100 sine 377 t, and the other one was 200 sine 377 t. Remember what this is right here. This is the angular velocity, omega, and it's equal to 2 pi f. So if the omegas match, that means the frequencies are the same. If the omegas are different, that means the frequencies are different. And what they're saying is the math I'm about to show you only works when the frequencies are the same. So if I have a sine wave basically coming from the same generator, then the frequencies are going to be the same and I can do this math. But if the frequencies are different, none of what I say here today will apply. We will always have situations where the frequencies are the same, so you can do the math. Now, I might give you one where they're different just to see if you're paying attention. And you got to tell me, hey, we can't do that because the frequencies are different. But anything that we can actually practically calculate, the frequencies have to match. So if I want to write a quantity in phasor form, I'm going to show you how to do that. So they got it on the paper, so let me just write it. The first thing to understand about phasors is there's only 2 types of phasors. There's only 2 types of phasors. I can have a voltage phasor. I can have a current phasor. Those are the only electrical quantities that I'm allowed to call phasors, a voltage or current. I can have a voltage phasor, I can have a current phasor. To express a voltage in phasor form or current in phasor form is really simple. It consists of two pieces. You write the magnitude, but that value right there has got to be in RMS. And then you write the phase angle. Okay? The magnitude in RMS and the phase angle. Now, let me tell you a little bit more about this phase angle. I just thought about something that I didn't show you. So let me erase this and let me go back to the sine thing that we talked about last time. So remember I have V equals V peak sine omega t. You know that, or you should know by now, that this right here is the instantaneous voltage or instantaneous value for voltage or current. This is the peak value or amplitude. And that right there is the angular velocity. That's how fast the coil is turning in the magnetic field. There's one more piece I can add to it though. I'm going to go ahead and do that. Plus or minus beta where beta is called the phase angle. That's the phase angle. So I can completely represent any AC waveform like this. Peak value, omega t, plus or minus the phase angle. So what is the phase angle? So let me, because you need that to do what we're going to do next. So what is the phase angle? Well, let's say I have a sine wave. I'm going to start it right here. Now I call this standard position. When I start it right here and go over the 360 degrees, I call that standard position. You know from, if I drop a line down here to here, you should know that that's 90 degrees. That's 90, that's 180, 270, 360, and so forth. So that's 90 degrees. Let's say that this sine wave is movable. I can slide it back and forth. If I could grab that sine wave and pull it back this way so that this point right here is on that axis, here's what it would look like. If I can pull it back so that this point is on the axis, that's what it would look like. And then this angle right here, I moved it back 90 degrees. That's what I mean by phase. Now you got to be careful here because, let me show you. Notice I have a plus minus sign there. So if I do this, if I say VP or V equals VP sine theta plus 90 degrees. So if that's a plus sign, what that means is I took the sine wave and I pulled it back this way. I pulled it in the negative direction. And that would be a phase angle, a plus phase angle. If I have a minus there, that means I started in the standard position and I pushed it the other way. So it's kind of counter the way you would think about it. You would think that if that's a plus sign, I'm pushing it towards the plus, and I'm pulling the minus towards the minus, but it's the opposite of that. If I'm adding a phase angle, that means I'm taking the sine wave and moving it to the left by however many degrees that is. In this case, it's 90. And if I'm subtracting, I'm pushing it to the right. So whatever you see here is the phase angle, and notice that this is in radians, but we always show that phase angle in degrees, because that doesn't change the value of anything. It just shifts the sine wave back and forth. So now, having said that, let me go back to what I said before. So if I want to show a phasor, the first thing to realize is there's only two types of phasors. You can have a voltage phasor and you can have a current phasor, and that should make sense because to express something as a phasor, you got to express the magnitude in RMS, and then you got to give the phase angle. And the only RMS value you can take is the RMS of something that has a peak value, and the only quantities that have peak value would be a voltage or a current. Those are the peak values that we talked about. So I can have a current phasor or voltage phasor, and all I got to do is write the magnitude and or as an RMS value, and I can write the phase angle is whatever it is. So if you understand that, then we'll do some practice problems. If you don't, I think you will once we do some practice problems. So let me show you how this is done. Number one, they give you a problem. And they want you to convert it to phasor form. So here's the problem. It is 50 sine omega t. And they don't tell you what omega t is because that's not necessary when you're dealing with phasors. Now I mentioned this last class. This is called time domain. So this is time domain. Because the independent variable here is t, and we're going to change it to phasor domain. So I want it in time domain. What I want is it written with a sign. In phasor domain, I got to have an RMS value and the phase angle. So let's convert this to a phasor. So to convert it to a phasor, now this is a peak value. What I got to do is get the RMS value. So how do I get RMS? I multiply by 0.707. So I see three icons out there. I don't know if it's just three people or not, but if you guys take out a calculator, give me the RMS value of this. 0.71 times 50 is what?
It's 35.
35.35.
And the angle. Now I don't have anything here, so I can just write the phase angle is 0 degrees. So as a phasor, this would be 0 degrees. That's my phase angle. Now it doesn't say that this was a voltage or a current. It doesn't say, but here, here's a voltage and here's a current, right? V represents volts, I represents current. To show that I have a phasor, you put this hat on top of it. So that's a phasor. That's a voltage phasor, and that's a current phasor. In books, they bold it, but I can't bold it on the board. So the way I'm going to show a phasor is by putting that hat on top of it. But they didn't specify here if this was a voltage or current, so I'll just leave it as is. So here's this number, this quantity, voltage or current, in time domain. Here it is in phasor domain. All right, so let's do another one. They give you 69.9 sine omega t plus 30 degrees. And they want you to convert that to a phasor. So again, I need the RMS value of this. Tell me the RMS value of that when you get it. What is it?
$49.41.
Angle, I just read it right there. It's positive, so it's going to be positive 30 degrees. And if that was a voltage, I put a V with a hat on it. If it was a current, I put an I with a hat on it. So you can see it's really, really, really simple. I just get the RMS value from here, and I get the phase angle from here, and I got the phasor form, the phasor domain. Now, this last one, let me talk about that one a little bit. Here's what this is. It's 45 cosine omega t. And I want you to write that as a phasor. Now, what you want to do here, you got to convert that to a sine. So, if you think about it, here's a sine wave. I don't know if you know a cosine wave, but when I shifted that over 90 degrees, that's a cosine wave. So a cosine wave, all it is a sine wave shifted by 90 degrees. So cosine theta is equal to sine theta plus 90 degrees. You want to remember that. Okay, so cosine theta is sine theta plus 90 degrees. So given this, I want to change it to a sine, and then I want to change it to phasor domain. So if I apply that, I'm going to write 45 sine. My theta here is the omega t. But to convert it to a sine, I got to add 90 to it, so plus 90. So this is equal to that as a cosine, as a sine wave. And once I get it like that, then I can put it in phasor domain pretty easily. So convert this to RMS for me. 0.707 times 45 is what?
31.82.
That will be 90 degrees. Okay? All right. Now, I don't know if we're going to run out of time on here, so I got to do problem number 4, but I think I'm going to do it next class. All right? I'll pick up with this next class because I think I got this set to cut off at 4:20. But let me say one thing. What we've done today, the phasor stuff is really, really important because think about this. Go back and remember what I said. What is RMS? What is RMS? RMS is the DC equivalent of AC. So what RMS does, it looks at heating effects. It just looks at, if I showed you the experiment with the thermometer in the water, it looks at, once you have an AC and an RMS value, it gives you the same amount of work as a DC value. So it renders AC and DC the same. There is no AC-DC heat. There's only AC-DC voltage and AC-DC current. Once we change that to heating effects, it's just heat. So once I get the equivalent heating effects, then basically I can treat AC as if it were DC. This is going to allow us to take AC waveforms and solve them just like we did when you had DC. Everything we did in DC, we'll be able to do in AC because this is like, when I change it to a phasor, it's like a DC value. So I don't know how to say it any other way than that. So we're going to run out of time. So we got one more problem. If you want to, you can try to do number 4 on your own. And then next time we get together, which will be Monday, we'll start off with number 4. But right now, make sure you study up on phasors. It's really simple. Phasor form. From here on out is going to be all phasors. We just do phasor stuff. Okay, so I'll have more to say about this next class. Does anybody have any questions for me before I sign off? I want to make sure that you guys send me your attendance. I don't know if you already did that, but today's the last. I got to turn it in tomorrow. So what you want to do is text me your first and last name, and you're in EET 131, and you're going to text it to 494-6162. So I need that for attendance. I gotta take attendance every day, but this is the one that counts. I gotta turn it in tomorrow. So if I turn it in and you're not there, you lose your financial aid. So we don't want that to happen. So text me. And guys, if you have any questions, go back and rewatch this video, watch the other videos. If you have any questions or comments, you can ask me, send me a text, and I'll be happy to deal with that. Other than that, if you don't have any questions, you guys have a great rest of the day. Have a great weekend, and I will see you on Monday.
The homework one is due today.
I'm not sure when it's due. It's the due date is on it. I got too many things to keep track of. So look on the blackboard, and it should tell you the due date. If it is due today, it's due at midnight. It's not due right now. So I usually set the due dates to be midnight.
All right.
Now you don't need any of this. You just need the sign stuff for homework one. So that's pretty easy. So check to see if it's due today, and go on and get that out the way. All right, guys. See you later.